Hi, we're Shafir and Yarden, both working at Sentinel-1. We're here to talk about a project we did recently whose purpose is to monitor the native 64-bit execution inside of WoW64 applications, which are basically 32-bit applications running inside of a 64-bit operating system. So we'll start with our personal embarrassing introductions. I'm Yarden. I'm a dancer, a gymnast, and acrobat. I started dancing and competing in rhythmic gymnastics as a kid and continued doing so for many years. In the past few years, I've become a circus acrobat, an aerialist, and on my spare time, I'm a security researcher at Sentinel-1, where I did this project together with Asaf. And I'll let him introduce himself.
So, hi everyone, I'm Asaf, and like she said, I'm a security researcher at Sentinel-1.
So before we start talking about the project, let's have a bit of background information. And AVs and security products in general want to monitor everything that's going on in the system and specifically inside of each and every process. A common way to do that is by using user mode hooks placed on interesting API functions, such as those that deal with memory management or inter-process communications. These hooks allow them to see every call to such functions and monitor what's happening inside of all of these processes. A major disadvantage of these hooks is that they can be quite easily bypassed by various different bypass techniques. We won't talk about most of these. There are about 1 billion. We'll focus on a specific family of bypasses that target the WoW64 mechanism. A couple of words about this mechanism. When Microsoft started developing the 64-bit operating system, they faced a problem. Existing 32-bit applications can't natively run on 64-bit environments and would generally break. Microsoft didn't want to break all the applications, so they had to find a way to allow them to still run. The solution they came up with is called WoW64, an acronym for Windows on Windows 64. It's a subsystem basically made up of a few 64-bit DLLs loaded into every 32-bit process, which allow the 32-bit application to run on top of a 64-bit environment as if they were running inside of a 32-bit environment. There are lots of different implications for this subsystem. For example, file system and registry redirection, which aren't very relevant for this project, so I won't talk about them. Another implication, which is relevant for this project, has to do with system call handling. Basically, whenever an application wants to ask something from the OS kernel, they do that through a mechanism called a system call. Most of the system calls are dispatched through a dedicated system DLL loaded into every Windows process called NTDLL. While 64 processes have two versions of this DLL, a 32-bit version and a 64-bit one. This is a simplified view of what this looks like. On the left, we have the 32-bit API function in 32-bit NTDLL. As you might see, it doesn't really do much. It basically just forwards the request to the WoW64 layer, which handles it. The WoW64 layer first has to make the transition from 32-bit to 64-bit mode, and does that through the jump instruction we see there in the middle. This is a rather unique instruction. It's a far jump to code segment 33. This instruction forces the processor on the hardware level to switch from 32-bit execution mode to 64-bit execution mode. Once we're in 64-bit mode, the WoW64 layer has to make a few more adjustments to the request, such as pointer size expansion from 32 bits to 64 bits, colon convention adjustments, since the colon convention is different on 64-bit mode, and a couple more stuff. Once it's done and the request is ready, it forwards it to a function with the same name in the second 64-bit NTDLL, which dispatches the system call through the dedicated CPU instruction. Now let's go back to a bypass I mentioned earlier. There is a whole family of bypasses that target the WoW64 mechanism, all work in pretty similar ways. The most well-known and most commonly used one is called Heaven's Gate. It was first published about 10 years ago, and since then was seen in the wild in lots of different types of malware as a bypass technique. How does it work? This technique makes the system call by calling directly to the 64-bit API function without going through the whole process we saw here. It does that by using the far jump or a similar instruction to transition itself from 32-bit to 64-bit mode, making all of the required adjustments and calling the 64-bit API function. The reason this is a bypass technique is because user mode hooks placed by security product are normally placed on the 32-bit API functions. As WoW64 processes are basically just regular 32-bit processes, it's much easier to hook 32-bit code, and normally there's no need to hook the 64-bit code because any interesting call will first go through the 32-bit API functions. That is, unless it was done using Heaven's Gate or a similar bypass technique, in which case the security product has a sort of a blind spot and it will miss any call done using such techniques. We want to address this problem by hooking the 64-bit API functions directly. This sounds easy, just do the same thing, but actually it wasn't as easy as we thought. First, we had to inject 64-bit code into the effectively 32-bit process. For that, we need an injection technique capable of doing that, so we'll see a couple of these. Then we can't just inject any 64-bit code, as it faces a few limitations when running inside of a WoW64 process. And finally, we actually need a hooking engine capable of working in such an environment, so we'll modify an existing one to allow it to run under such conditions. Well, that was the introduction. Let's start with the injection.
Okay, so just like Erden said, the first task that we must accomplish is to find a suitable injection method which will allow us to run our own 64-bit code in the context of the target WoW64 process. So generally speaking, there are lots of very different injection methods which are available at our disposal, but unfortunately, most of them aren't very beneficial to us, and the reason for that is that most injection techniques would only allow us to inject the DLL which has the same bitness as the target process. So that means either injecting a 64-bit DLL into a 64-bit process or a 32-bit DLL into a 32-bit process. And what we needed in the course of this project is something a little bit more unique. We actually needed the ability to inject a 64-bit DLL into a WoW64 process, which, just like we have said, it's effectively a 32-bit process. So not any injection method is capable of doing it. Okay, so in the course of this talk, we are going to describe 3 relatively known methods which are capable of injecting 64-bit DLLs into 32-bit processes. We will start with the relatively easy stuff and gradually work our way through to more complicated techniques. We will conclude this phase by talking about an injection method called injection via APC. And we will see that while this specific technique works great on some of the older Windows platforms, for example, Windows 7, it would probably break when you try to run it on more modern platforms such as Windows 10. So after we will dig in a little bit into the root cause of this failure and analyze it, we will be able to present 2 new variations developed by us during the course of this research, which basically allows this specific injection technique to work perfectly even on the latest release of Windows 10, for example. So this is our agenda. So let's start with the easy stuff. So the first technique I'm going to describe was actually discovered several years ago by a security researcher named Walid Asar, and it basically revolves around hijacking of a DLL named WoW64 log.dll. So what is this DLL anyway? So whenever I launch a new WoW64 process in the system, an integral part of its initialization phase is going to look up and load a 64-bit DLL named WoW64 log directly from the system32 directory. Now, this DLL is not shipped by default as part of the standard Windows installation, which makes us and many other security researchers in the community believe that this DLL is actually only used internally by Microsoft in order to aid debugging or diagnostics of WoW64 applications. And in fact, we can leverage the fact that this DLL is not shipped by default in order to gain code injection. The way we do this is by simply creating our DLL, renaming it to WoW64 log, making it export a specific well-defined set of functions, and then just drop it to the system32 directory. And once we have done so, our DLL will be like magically loaded into every new WoW64 process in the system, and thus we've gained our code injection capabilities. So to summarize, a really easy and straightforward DLL hijacking technique. Okay, the second technique we are going to describe actually takes advantage of Heaven's Gate. So if you recall, not long ago, Yarden talked about Heaven's Gate and basically described it as some sort of a hook bypass technique, which is used mostly by malicious actors in order to bypass hooks inserted by various security products. But reality is sometimes a little bit more complex than that. And there is usually like a very fine line which separates malware from security products. And I think this is one of the cases in which the very same technique can be beneficial for the attacker as well as for the defender. So with that in mind, let's see how an AV, for example, might benefit from Heaven's Gate. So what we must understand is that every WoW64 process has in it two distinct image loaders. One implemented in the 32-bit NTDLL, which can only load additional 32-bit images, and one implemented in the 64-bit NTDLL, which can only load additional 64-bit images. So now, for the sake of argument, let's assume that I already have 32-bit code running inside the target WoW64 process. Again, if we're talking about a security product such as an AV, this is a valid assumption which usually holds. So this 32-bit code can normally only access the 32-bit image loader, which isn't really getting me anywhere because I can't use this loader to load my desired 64-bit payload. But what this 32-bit code can do is use techniques such as Heaven's Gate in order to transition itself into 64-bit mode. And once the jump into 64-bit mode has been made, it basically opens up the possibility of using the 64-bit loader, for example, by calling the 64-bit version of a function named LDR-LOADDLL, and I can use this function to load my desired 64-bit payload. So to summarize, we are basically talking about a two-phase injection method here, in which in the first phase, we inject a 32-bit DLL, use this DLL to transition into 64-bit mode, and then load an additional 64-bit DLL. Okay, the third and last injection method we are going to describe is something called injection via APC. So before we dive into all of the nitty-gritty details of how this injection is actually implemented, a couple of words about APCs in general are usually in place. So an APC is an acronym which stands for Asynchronous Procedure Call, and it's a mechanism built into the Windows kernel, which basically allows me to take a particular routine and then queue it to a thread of our choice. And what this mechanism guarantees is that at some point in the future, the target thread is going to stop whatever it is currently doing and instead jump to my routine instead. So in Windows, APCs come in several flavors. In the course of this talk, we're only going to describe one specific kind, which is called user mode APCs. So user mode APCs have some distinct characteristics to them. First and foremost, the function that is about to be executed is going to run with user mode permissions, unlike kernel mode permissions. The second key characteristic is that in order for the APC to trigger or fire, the target thread must enter something called an alertable wait state. So that happens, for example, when the thread goes to sleep, waits for a synchronization object or something like that. The third key point to notice is that all user mode APCs are first handled by one single function called kuser APC dispatcher, which is exported from NTDLL. So this function basically is going to make several preparations and then just jump to the function which the programmer intended to call. And we will get back into this function later. We have a few possible options for queuing an APC. The most common one is to use a kernel mode driver to do it. We can do it also from a user space application, but we are going to stick with the kernel mode variation. Okay, so now let's talk about the injection itself. So injection via APC is probably the most popular injection method used both by AVs as well as by some intelligence agencies, as you can see. And they do this by simply queuing an APC, which ultimately calls a function such as LDR-LOADDLL, load library, or one of its variants. And indeed, in most cases, this technique is only used in order to inject a DLL which has the same bitness as the target process. But what we should keep in mind is that in WoW64 processes, APCs can run both 32-bit code or 64-bit code, and in some cases, for example, when we queue our APC from a kernel mode driver, the default will be to run it in 64-bit mode, and that makes them great candidates for loading additional 64-bit DLLs. Okay, what we can see here is basically some kernel mode code which implements this technique, DLL injection via APC from a kernel mode driver. So some key takeaways from this slide. First of all, let's talk about the function which is going to execute in the context of the APC. So all of these functions must conform to a standard prototype, which was already predefined by Microsoft. And as you can see, all of these functions must return void and receive 3 pointers as their input arguments. So that raises the question, what happens if the function that I wish to call has a different prototype? So in order to overcome this obstacle, we use some sort of a trick. And the trick basically says that we are going to use the first parameter, the normal context parameter, in order to pass in a user-defined structure. And inside this structure, we can encapsulate both the address of the function that I really wish to call, as well as the values of all the parameters that I wish to forward into it. So in our case, because we are dealing with DLL injectors, the function is going to be the 64-bit version of LDR low DLL, and the parameter is basically going to be the name of the DLL I wish to inject. So if we take a look at this function in its entirety, we can see that it basically just translates one function prototype into another function prototype. And this is the reason we chose to term it an adapter func. This is not an official terminology of any kind, but this is the term we are going to use throughout the rest of this talk, so keep that in mind. Now, the type of the APC we are using is a user mode APC, which means the adapter func itself must reside in memory which is accessible to user space. So in order to make sure it does, we first have to allocate a user mode buffer, which is both executable as well as writable. And after we get this buffer, we can simply copy into it the actual code bytes which comprise the adapter func. After we do this, we can simply initialize the APC object to point to the buffer we have allocated and queue it to the APC queue of the target thread. Now, from our kernel mode driver, we can intercept thread creation event and basically repeat this entire procedure for every newly created WoW64 thread in the system. And this ultimately means that our DLL will be injected into every WoW64 process across the system. Okay, so we have taken the source code that I've just shown you, compiled it into a driver, loaded it into, I think, a Windows 7 system and tested it. And indeed, as you can see, it worked quite well. We have a 32-bit process to which we managed to inject our own 64-bit DLL. So this was kind of nice. But after some time, one of us said it would be like a good idea to test the same solution on a more recent Windows version, for example, Windows 10. And then we got some very different results. Specifically, most of the processes to which we tried to inject our DLL simply crashed. So after a little bit of debugging or probing on Twitter, we bumped into this tweet from Alex Ionesco. And from this tweet, we learned several interesting facts. Specifically, we learned that the crash is probably related to CFG. So before we can start thinking about possible solutions to our problem, we first have to understand what CFG is, what are its implications across the system, and how it is related to WoW64.
So for those of you who don't know this feature, CFG is an acronym for Control Flow Guard. It's a relatively new exploit mitigation technique introduced by Microsoft in Windows 8.1 and enhanced in Windows 10. This is a compiler-enabled mitigation that is meant to prevent memory corruption vulnerabilities by preventing indirect calls to non-legitimate call targets. It works by inserting an additional call to a validation routine before every indirect call done in the application, as you can see here. This validation routine receives a single argument, which is the address that is about to be called indirectly, and checks whether or not it makes a valid call target. If the address is a valid target, the function returns and the execution continues normally. If the address is not a valid call target, this validation routine will just crash the process. What are valid call targets? For images compiled with CFG, they export a list of where their functions are. So the valid call target is, forgot to say that, the valid call target is defined as the beginning of a function. So we have this list of functions, and we know where the valid call targets are for this image. But for images not compiled with CFG or private memory allocations, we don't have this list. So the whole executable buffer is just considered a valid call target just to be safe. The way CFG knows where these valid call targets are is by using a memory area designed for this purpose called a CFG bitmap. In this bitmap, each bit marks 8 bytes in the process memory and shows whether or not these 8 bytes make a valid call target or not. This is a very large memory area, so most of the time, a large portion of it is not used, and only whenever new executable memory is introduced into the process, the relevant part of the CFG bitmap is committed and marked to show which parts of it make a valid call target and which don't. Now let's take a look at the validation routine. This is LGRP validate user call target found inside of NTDLL. This is a function that gets called whenever an indirect call is about to be made, this function receives the address that is about to be called and makes the arithmetic calculations required to find the bit in the CFG bitmap that marks this address. Then it checks if the bit is set. If the bit is set, it means that the address is a valid call target, so we take the left branch and the function returns. If the bit is not set, meaning this is not a valid call target, we take the right branch, the function will eventually crash the process, resulting in the gorgeous call stack we have here that we took from our crash dump on Windows 10. In WoW64 processes, CFG gets a tiny bit more complicated. Since WoW64 processes can run both 32-bit and 64-bit code, we have two CFG bitmaps. WoW64 bitmap that marks the 32-bit code in the process, and a native CFG bitmap that marks the 64-bit code. I think I said it correctly. We also, as you might remember, we also have two versions of NTDLL, a 32-bit and a 64-bit version. So we also have two versions of the validation routine. And it works that way. The validation routine in the 64-bit NTDLL checks addresses against the native bitmap, and the validation routine in the 32-bit NTDLL checks addresses against the WoW64 CFG bitmap. A new executable memory in WoW64 processes only ever gets marked in one of these two CFG bitmaps. So how do we choose which bitmap to mark? Well, for that, we have this function, miSelectCFG bitmap. This is a kernel function called whenever new executable memory is introduced into any process. This function chooses the correct bitmap to mark this memory in based on a few simple checks. First, the process must be a WoW64 process. If it isn't, the process should only have one native CFG bitmap, so it will always be returned. Second, if we are running a WoW64 process, the address must be below 4 gigabytes. In WoW64 processes, actually, most of the memory above 4 gigabytes is reserved and we can't access it or allocate it normally. So this check should always, almost always come true in WoW64 processes. And finally, we have this check, which actually tests whether this memory is part of an image or a private memory allocation. Private memory allocations done in WoW64 processes will always be marked in the WoW64 CFG bitmap, regardless of who allocated them or for what purpose. Now, if this memory is part of an image, we check whether this image is a 32-bit or 64-bit one and choose the bitmap accordingly. Now, how does this all relate to our crashes? Well, let's rewind a bit. We took another look at our crash dumps and saw that we managed to queue our APCs to WoW64 processes and actually got to KUser APC dispatcher, which is the function in NTDLL that should dispatch our APC and call our adapter thunk. But instead of calling our adapter thunk, this function first called the validation routine, since APC dispatching uses indirect calls, and the validation routine never returned. Instead, it crashed our processes. But why did that happen? Well, as you might remember, private memory allocations in WoW64 processes always get marked in the WoW64 CFG bitmap. But the function that should dispatch our APC is a function in the 64-bit NTDLL, which checks addresses against the native CFG bitmap. So our adapter thunk is sort of marked in the wrong CFG bitmap. It's not marked in the native bitmap. So the validation routine assumes it does not make a valid call target and crashes all of our processes. This seems to put an end to our APC injector in Windows 10, but we kind of like this solution and didn't want to give up on it just yet. So now I'm going to do what I usually do in such cases and ask Asaf to solve the problem.
Okay, so at this point, we took another closer look at miSelectCFG bitmap and realized that if we want our adapter thunk to be marked as a valid call target in the native CFG bitmap, we have to make this large if statement evaluate to false. So we first decided to tackle the first subcondition because it seemed like the easiest one to manipulate. So the first subcondition actually checks whether or not the current process is a WoW64 process or not. And it does so by probing one of the members of the relevant eProcess structure. So this member is actually a pointer. And if this pointer is set to null, the kernel thinks we are dealing with a native 64-bit process. Otherwise, the kernel assumes we are dealing with a WoW64 process. So with that in mind, we came to some sort of a DCOM-based solution, a direct kernel object manipulation solution, in which right before we allocate memory for our adapter func, we simply go out to the eProcess structure, reach this specific member, and just zero it out or nullify it. And this will basically trick MISelect CFG bitmap into thinking that we are allocating executable memory in the context of a native 64-bit process, and thus our adapter func will be marked as a valid call target in the native CFG bitmap. Of course, that after memory for the adapter func has been allocated, we should restore the original value of this pointer, otherwise bad things might happen. So to summarize, this option basically works by temporarily nativizing a WoW64 process, and while it does do the trick, it suffers from some serious downsides, mainly because the eProcess structure that has to be modified is largely undocumented and changes often between Windows releases, so this makes the offset of the member we wish to modify from the beginning of the structure to be inconsistent, so we can't rely on it. And this is some sort of a solution which tends to break over time. So taking all of these downsides into consideration, we decided to look for an alternative solution, hopefully one which doesn't require making modifications to undocumented kernel structures. So at this point, we decided to mentally zoom out and really rethink about our problem in the first place. So to recap so far, we have a APC injector, which works by allocating an adapter func. And the problem is caused by the fact that our adapter func is marked in the WoW64 CFG bitmap. But if you recall, the only reason we have an adapter func to begin with is to basically just act as a middleman, which just forwards the calls to the 64-bit version of LDR low DLL. And the 64-bit version of LDR low DLL is obviously marked in the native CFG bitmap. So this made us wonder, why do we really need an adapter func in the first place? Or to put it in other words, why can't we just initialize our APC to point directly to the 64-bit version of LDR low DLL? Okay, so on the surface of it, it looks like we have some sort of a problem. On the right-hand side, we can see the function prototype, which is shared by all user mod APC routines. We have seen this one before. And like we've said, all of these functions receive 3 pointers as their input arguments. And on the left-hand side, we can see the function prototype of LDR low DLL, and it happens to accept 4 arguments. So at the very least, we have here some sort of a function prototype inconsistency issue. So does this mean we have to give up on this idea? Not yet. And what might actually work in our favor is the x64 calling convention. So like some of you might know already, in x64, almost every function receives its first 4 arguments via registers. The first parameter is passed in the RCX register, the second one in RDX, the third in R8, and the fourth one in R9. Now, if we initialize our APC to point directly to LDR low DLL, we will have direct control over the values of the first 3 parameters. But unfortunately, we won't have any control over the value of the last, the 4th parameter. And what will happen is that by the time LDR low DLL will be called, whatever value happens to be loaded into R9 will be interpreted as the 4th so-called missing parameter. Okay, so now let's take a closer look at LDR low DLL and specifically at its 4th parameter. So as you can see here, the 4th parameter is actually annotated as an output parameter. And it's basically a pointer to which the function is going to write the base address of the DLL that it has just loaded. So this kind of makes things a little bit more complicated because it means not any value loaded into R9 will suit our needs. And more specifically, it means that R9 has to be a pointer to a writable memory block. And moreover, this memory block has to be some sort of a scratch space because we cannot overwrite important information in the process without risking in crashing. So now, the million-dollar question is what value will be held by R9 by the time LDR low DLL gets called. So in order to answer this question, we had to perform some reverse engineering on K-user APC dispatcher. And after some reversing, what we found out is that right before K-user APC dispatcher forwards the call to the target of the APC, which in our case is LDR low DLL, it is going to load R9 with something, with a pointer to something called a context structure. This context structure basically encapsulates the CPU state that is about to be resumed via the call to anti-continue you can see here once the APC dispatching process has finished. Now, because we know LDR low DLL is going to interpret R9 as its 4th parameter, it basically means it is going to overwrite the first few bytes of this structure with the base address of the DLL that it has just loaded. So generally, this doesn't sound like a very good idea because we are overwriting CPU information that is about to be resumed later. But luckily for us, what happens, at least on the x64 architecture, is that the first few members of this context structure don't really hold members which are CPU related. So we can override them safely because we know they won't be used later by anti-continue to actually restore the context. So to summarize, what we found out is that we can get rid of the adapter func entirely and instead just initialize our APC to point to LDR low DLL. So we have modified our injector accordingly, compiled it into a driver, loaded it this time into a Windows 10 machine. And as you can see, we indeed managed to inject our 64-bit DLL to a 32-bit process which is CFG aware.
Have a working injection method, or more like 3, a couple of them even work on Windows 10, we can move on to a second part of this project, which is the hooking. We start this project by wanting to hook 64-bit API functions inside of WoW64 processes. So for that, we need a hooking engine capable of doing that. A hooking method, which is very common in hooking engines, and also the one we used here, is called inline hooks. This method works by overriding the first few instructions of the hooked function and replacing them with a jump instruction to a memory buffer we allocate inside the process called trampoline. This trampoline just forwards the call to our detour function found in the DLL we have just injected. Our detour function can basically run whatever code we want it to, either before or after, eventually calling back into the original function. When we call back into the original function, we first have to call into the trampoline in order to run the missing instructions that we wrote over in our hooked function. Then we jump back into this hooked function to allow it to resume its normal execution. There are lots of hooking engines that implement this technique, but unfortunately, while doing this research, none of the hooking engines we inspected was capable of running inside of a WoW64 process, or running as a 64-bit hooking engine inside of such processes. But what's the problem? Well, anybody who wrote code for Windows might know a few basic DLLs that implement most of the Win32 API. These DLLs are stuff like kernel-based, kernel32, C runtime libraries. They're very basic when writing code for Windows, and all hooking engines we looked at use them. But the 64-bit versions of these DLLs are simply not loaded into WoW64 processes, and because of some technical issues, we generally can't load them in either. So the first thing we had to do when modifying our hooking engine, we chose an existing one to modify, was to get rid of all of these dependencies. Actually, the only DLL we could rely on was the native anti-DLL, which we knew was always loaded into WoW64 processes. So we had to get rid of all external dependencies other than the native anti-DLL. The major thing we had to do there was re-implementing all Win32 APIs that were used by our hooking engine. For example, here we have our implementation of virtual protect, a function exported from kernel 32. In this example, you can see our implementation of this is basically just a forwarder to NT-protect virtual memory exported from NTDLL, so we can use it. Most of our implementations looked something like this, so they were pretty easy to achieve. A few were a bit more complicated, and then we had either to reverse engineer the missing functions or go to the ReactOS sources and do whatever they did. After we re-implemented all Win32 APIs in the hooking engine, we tried to recompile our DLL with the hooking engine and got this great list of errors. This looks pretty threatening, at least it looked like that to us, but actually most of these are just errors requiring slight configuration changes, like disabling some checks that use C runtime libraries, which we don't have. So this is all very technical and honestly not super interesting, so I'm not going to go into too much detail here. After we made all of the configuration changes required to fix that. We recompiled our DLL and actually managed to compile a 64-bit DLL, which includes a working hooking engine that only relies on the 64-bit NTDLL. So we injected this DLL into our 64 process on Windows 7 and saw that we can successfully hook any API functions we wanted in the 64-bit NTDLL. Then we tried it on Windows 10, and then it didn't do so great. So what happened here? Well, the memory layout in WoW64 processes is slightly different between Windows 7 and Windows 10 machines. Basically, in Windows 7, all of the memory above 4 gigabytes is reserved in WoW64 processes, so we can't allocate it, we can't use it, and all of our DLLs, all of our code is found below 4 gigabytes. On Windows 10, that's almost the case, only the 64-bit NTDLL was moved above 4 gigabytes to a much higher address. But other than the native NTDLL and the native CFG bitmap found right next to it, the rest of the memory above 4 gigabytes is still reserved and we can't access it. Why is that a problem? Well, the jump instruction that we use to overwrite the prologue of the hooked function is actually a relative jump that receives a 4-byte offset. What this means is that this jump can only pass a distance of up to 2 gigabytes from our hooked API function to our trampoline, which we allocate ourselves. In Windows 7, that's fine. We can allocate our trampoline right next to the native NTDLL and usually have a distance of way less than 2 gigabytes to go through. But in Windows 10, we can't allocate our trampoline next to the native NTDLL. It's loaded way above the 4 gigabyte line, and we can only allocate our trampoline below 4 gigabytes. Since the total address space in 64-bit processes is 128 terabytes, we're likely to have a distance of way more than 2 gigabytes to pass. So we're going to need to replace our jump instruction with an alternative form of jump, preferably one that allows us to pass to jump into an absolute 64-bit address.
Okay, so at this point, we compiled a list of some branching sequences which are valid on the x64 platform. So let's just go over them one by one and see what might fit our requirements and what not. So the first option you can see here is actually the relative jump, which is already in use by most hooking engines. And like Erden said, this form of jump works on a D-word size operand, meaning it can only pass a distance of up to 2 gigabytes in every direction. And like she said, the 2 gigabytes are simply not enough for our case, so we had to discard this option almost immediately. The next two options work by loading a register with a 64-bit absolute address, either by loading it with an immediate value or by a reference to a memory location, and then just branching to the address held by the register. And while these two are both perfectly valid solutions, they suffer from the same problem. They both dirty up a register, which kind of makes things a little bit more complicated for us because we later have to restore the original value of it. So at least for the first iteration, we wanted to keep things as simple as possible, so we had to give up on these two as well. The fourth option is actually quite interesting because it doesn't use the jump instruction. Instead, it builds an address onto the stack and then just returns into it. Again, for the first iteration, it seems a little bit tricky, so we decided to put it aside, and a quick spoiler alert, we will probably get back into this later. So for the first iteration, it basically left us with the fifth and final option, which takes advantage of an addressing mode called RIP relative addressing, and it basically just jumps to the 64-bit absolute address, which immediately follows the jump instruction in memory. So we have modified our hooking engine to use this kind of jump, compiled it, bundled this entire thing into a DLL, injected it, and this time what we found out is that our hooking engine works only on Windows 10, but not on earlier versions of Windows. So in order to investigate this thing and get a root cause analysis, we decided to take a copy of NTDLL from Windows 7, for example, a copy of NTDLL from Windows 10, and then do some sort of a binary diffing and just see if there is anything suspicious which pops up. And what we found out is that in Windows 7, for example, all functions to which we wish to apply our hooks are significantly shorter than their Windows 10 counterparts. So why is this a problem? because the form of jump that we have chosen, this one, is actually quite long. Its binary encoding takes up something like 14 bytes, if I recall correctly. And in Windows 7, for example, the functions are simply not long enough. We don't have enough bytes in the function to overwrite. So this is the root cause of the failure we have encountered. So this failure kind of took us back to the drawing board, and we decided to give another try to the fourth option, the one which works by building the others onto the stack. So as you can see here, this option is actually comprised out of 3 different instructions. We first have the push instruction, which takes care of setting up the low-order D-word of a 64-bit absolute address. It is then followed by this move instruction, which sets up the high-order D-word of the same address. And it then concludes with a ret instruction, which just pops up an 8-byte value from the stack and returns into it. So in its current form, this sequence of instructions is again too long for us. I think it's even longer. It takes up 16 bytes, if I recall correctly. So in its current form, it's not going to get us anywhere. But we started to thinking, how can we optimize this solution? And after a little bit of trial and error, we managed to understand that we can get rid of the move instruction entirely and still be left with a working solution. So let's understand why is this possible. So like we have said several times during the course of this talk, in WoW64 processes, we normally can't allocate memory above the 4 GB boundary because the address space there is simply reserved. Now, because the trampoline is itself a private memory allocation, it will always be allocated below that line. And that means that if we take, for example, an address of a trampoline, we can split it into 2 distinct D-words, where the low-order D-word will hold some arbitrary value, and the high-order D-word will always be zeroed out. And what works in our favor in this case is just x64 assembly, because whenever I use the push instruction to push a 32-bit immediate value, what will actually happen is that the CPU is going to push 64-bit value onto the stack, because the stack always has to remain 8-byte aligned, and the high-order D-word is going to be zeroed out by default. So this is exactly what we need. And actually, after we get rid of this move instruction, we are left with a much shorter sequence, which only takes up 6 bytes. And this kind of makes this solution a universal solution because it works on all Windows versions starting from Windows 7 up to and including Windows 10. So we have, again, modified our hooking engine to use this kind of jump, compiled this thing, bundled it into a DLL, injected it, and so forth. And this time it just worked quite well. And if you, for example, try to disassemble one of the hooked functions prologue, you will see something like that, a push, which is immediately followed by a ret.
Okay, so to summarize, let's have a quick recap of this talk. First, we needed an injection method capable of injecting 64-bit DLLs into WoW64 processes. We started with a few previously known methods and improved our APC injector to make it work on new Windows versions as well. Then we moved on to the hooking engine. We took an existing one, in our case we used MinHook, and modified it to allow it to work on inside of WoW64 processes. First we had to strip it of dependencies other than native NTDLL, and then we had to replace the jump instruction normally used by hooking engines with, in our case, a push ret solution to allow it to work on all Windows versions. That's it from us. We also published this research in a series of blog posts if you want to have more detailed information. And for anybody who's interested, we published our modified hooking engine in this repository here. Questions, of course, you're free to ask us also later or through Twitter, email, whatever. Okay, so that's all from us.
Thank you very much, Asaf and Yarden. Are there any questions from the audience? Okay, if there are no questions, then do keep in mind that they will be here all day, so you can ask any questions that comes to mind to them afterwards. Thank you very much, and give it up one more time for Asaf and Yarden.